Time for a new topic. That means it'll be a little easier in some ways, but at the same time we have a little background material to pick up. So the section itself is pretty straightforward, but if you haven't seen linear algebra before, we do have to review a bit of that. We're going to talk about systems of differential equations, and these just basically means a bunch of differential equations. Here's some applications. You can see how these things naturally arise. You can have a solute travel in a solvent, like pollutant in water or something like that, or salt in water, and go between different compartments. They use these in models of the Great Lakes to model the flow of pollution around, or you can model the flow of a medicine in the bloodstream, that kind of thing. Population models often have these. You've maybe heard of predator-prey models where the predators and the prey compete. There are differential equations for those. Vibrating structures such as bridges and so forth, they're like multiple masses on springs and they move together and the thing shakes, and certain vibrational frequencies can knock the bridge down, and you can figure them out with differential equations. Lots of other things in engineering. Control systems are that way. Circuits that have multiple loops are systems of differential equations. We did the circuit problem with one loop. Now what if we have multiple ones that leads to systems? So this is where we're going with this, and we just want to do a brief introduction. We're really only interested for this class in linear systems of differential equations. And we'll just say this then. Here's how they often write systems of nonlinear equations. The idea of a system of linear equations is simply that every equation in there is linear. And so we'll show what that form looks like in a second. But for general linear equations, they're often written in this form. If you have n independent variables instead of one, you can write d1, du1, dt. u1 is a function of t. And if there's an equation relating that derivative to u1 through un, all functions of t, and t, and then similar as derivative of u2 with respect to t is a function of t and u1 through n, and du and dt is a function of t and u1 through un. The idea being that each of these u's is a function of t. What are the functions of t, u1 through un, that satisfy this list of n differential equations in the n unknown dependent functions u1 through n? What could it be that satisfies that? The most interesting case is where there's the same number of unknowns u1 through un as there are equations. Now to write these systems, we really want to go back to do matrices, and some of you maybe haven't seen very much of these, so we'll do a little introduction to that. When I write a boldface u here, it represents a vector, u1, u2 through un. This t here means transpose. It means you really want to write it as a column going down like that. And so when you put the t up here, it means it's a column vector, we call it. And then f of tu could be a vector of these functions. F of tu and tu and tu. And each of these vectors here, u should be bold, is a function, is the vector of u's. And so now you can write this whole system in this compact format. Du dt means the derivative component by component of this vector, so it's these components, du1 through dun dt. And f on the right-hand side refers to this vector of n components, this one right here. So there's how you can write using this vector form these things very compactly. You've seen vectors in calculus, so this shouldn't be anything new. It's just this transpose here means turn it sideways, and same thing here. All right, so you can write this big system of n linear equations, n differential equations in n unknown functions u1 through un. That briefly. Now, how do you know when it's linear? That's the case we're really interested in here. We're going to try and solve some of these linear systems. But nonlinear systems are of great interest too. If you go in and take a second course of differential equations, you'll consider those. We'll say that a first order system differential equations like that in differential equations is linear if each of the equations can be written like this. Well, that's what we were talking about before. A function of t times u1 plus a function of t times u2 plus a function of t times un plus a function of t only. Like, that it looks just like what we wrote for first order equations was this, single equations was this, when there was only one dependent function u1 of t. We wrote it like that. And now what we're doing is just letting a function of t multiplying each of the u's. So it's the same kind of concept as before for a single equation, just with more terms, one for each of the u's. Similarly, this equation is a linear equation. Here's what we wrote for single equations, du2 dt is a function of t times u plus a function of t. Now we let a function of t multiply each of these, and same thing all the way down. That'll be a linear a linear first order system. First order because only the first derivative exists. That's the highest derivative. So this will be a linear system of first order equations if you can write it in this form, not just the other form. Now, when you do this, we can put together what's called a matrix, right? A matrix is a rectangular array of numbers. But what we're really going to talk about here is a matrix valued function. Each component here in the matrix, the idea is there's A11, A12, A13 up to A1n, n columns here, and n rows, A11, A21, A31, N1. You've seen a little bit of matrices in calculus already. Remember, we took determinants of matrices and so forth to calculate Jacobians and those kinds of things. So the matrix is just a rectangular array of numbers that, like you've seen before, and we're only interested in square matrices, those that have the same number of rows as columns. So we'll call it an n by n matrix if it has n rows, the rows go across this way, and n columns going down this way. And we'll number them in the usual way. A11 is the element in the first row, first column. A12 is first row, second column. A1n is first row, nth column. And so here's a matrix valued function. We did vector valued functions in calculus 4, recall. Each element can be a function of t, but when you put in t, then you get a rectangular array of numbers. And then f of t is a vector. You're familiar with vectors, a vector valued function. Put in t and you get a list of n numbers in there. All right, so that's the brief notation, because if we write it this way, if we make these definitions that A denotes this n by n array of numbers and F denotes this n row, one column, n by 1 vector. A vector, by the way, is just an n by 1 matrix. It's a matrix with one column, or you can have a row vector with one row. And so if we have an n by n matrix, a square matrix, and an n by 1 matrix, a vector of length n, then we can use this notation to write linear systems if you think about it. But we first have to introduce this thing here, which is a matrix multiplying a vector, and then a vector addition. You've added vectors before, but maybe you haven't done matrix multiplication before. So we can write this system in this very simple form. Du dt equals A of t, a matrix valued function, times u. I suppress the of t on u just for brevity. A lot of books do that. But u is a function of t that's unknown at this point. So we'll suppress the of t on the unknown function. And this just stresses that the matrix valued function and the f of t in the equation can depend on t. All right, well, let's take a look at matrix multiplication to see why we can write it that way. Here's the idea. If you have a matrix, 2, 3, minus 1, 0, here's a 2 by 2 matrix. We could multiply it by a vector, maybe, and it has to be compatible for multiplication. We'll say that an n by n matrix can multiply an n by 1 vector, and it works like this. You take this times this, plus this times this. So this times this plus this times this. And you get back 2 times 2 plus 3 times 4 out of that. And then, so you're taking this row with the vector. Now you take this row times the vector, minus 1 times 2 plus 0 times 4. Now what you get out is, let's see, 4 plus 12, 16, right? And minus 2 plus 0 is minus 2. So we say the product of this matrix with this vector is 16 minus 2. And in general what you do, you don't have to use square matrices. You can use an m by n matrix, m rows and n columns, and multiply it by an n by 1 vector, and you get back an m by 1 result. That's most generally when matrices aren't square. We're only interested in n by n matrices, and so we're going to take like this is a 2 by 2 matrix, and we'll get this result when we multiply, for instance, a 2 by 2 matrix times a 2 by 1 vector. The key is these have to have, this has to have the same number of columns as this one has rows, and when they do, they're compatible for multiplication. The output is the number of rows of this one, number of columns of this one. That's most generally in matrix multiplies. We don't care about that. We're interested only in square matrices multiplying vectors that have the same number of rows as this one had columns. So we'll multiply, in this case, a 2 by 2 matrix times a 2 by 1 vector and get back a 2 by 1 vector, right? And so we say the product of this matrix and vector is this vector. And then we can add vectors in the same old way that we did in calculus, right? Minus 3, 1, plus 2, 6. Vectors are just added component by component. So we take minus 3 plus 2 is minus 1, and 1 plus 6 is 7. Easy, right? So this is all very easy. But this definition of multiplication, where you take the dot product, right, of this row with this column, this times this plus this times this, and put it first, and then the dot product of this row with this column, this times this plus this times this, and put it as the second entry, is how we define matrix multiplication. And then it allows us to write our systems of linear equations simply. So I haven't gone into a lot of matrix theory because we don't need a lot for this. But here it is. When you have a linear system, you can always write in this form du dt equals au plus f, or this is a matrix multiply. And then your notation is a lot easier. And if this vector f of t is the zero vector, all components equal to 0, then you say it's homogeneous and you can write it in this form. You don't need to add the zero vector, it doesn't add anything, right? So there's a homogeneous system if it can be written without the f added on the end. Alright, now what happens is there's a nice existence and uniqueness theorem for these things. If you also have n initial conditions with a system of n linear first order equations and n unknowns, and we're only interested in first order equations, it turns out. There are higher order equations, again that's for a later class, we're doing an introduction. If you have that, the first function you're looking for, u1 evaluated at some point t0 is some number u01. The second component at t0 is some number u02, all the way to the nth component is equal to some number in u0n. So each of the unknown functions has a given number at the same value of t equals t0. We can write that in vector form like this, right? The function u of t evaluated at t0 is equal to this vector u0 of length n. Again, these are column vectors. I put the transpose notation here, t, to indicate that. I'm just trying to write them this sideways here to save room. A single initial vector like this, we call this an initial condition on the system, under nice conditions determines a unique solution. What are those conditions? Well, it's on the next page. This theorem, it's very easy, and it's very much like your theorem for first order equations with an initial condition. In fact, that's a special case of this one. A linear initial value problem, meaning a differential equation together with an initial vector of n first order differential equations for n unknowns with n initial values, in which the n by n coefficient matrix A of t and the n by 1 vector f have continuous elements. Right? Each of these a11 through ann's and each of these f1 through fn's are continuous functions on some interval I of t values containing the initial point t0. That's all you take. All it takes, you have a unique solution. So a linear system like this, where a and f are continuous, and you have an initial vector, has a unique solution on that interval in which they're all continuous. I'll refer you to a text like Nagel, Saff, and Snyder. Differential equations is my favorite text. For the proof of that, they have it way in the back if you ever take an interest. But let's look at this. This is a linear system together with initial values. du1 dt equals this function of t times u1 plus 1 times u2 is a function. When I think of 1 as a function of t, it doesn't have to have t in it. It just means it doesn't depend on the u. So here's a function of t times u1 plus a function possibly of t times u2 is du1 dt, and then du2 dt is 1 times u1, a function of t times u1 plus a function of t tangent times u2. This is a system of two linear equations and two unknowns. Here's your initial values. u1 of 1 equals 1, u2 of 1 equals minus 1. We can write this in matrix form like this. There it is. du1 dt, du2 dt equals this matrix times this vector plus nothing, because there's nothing added on functions of t alone. And then the two initial conditions can be written in vector form like this. Just put the first one on the first line and the second one on the second line. u1 of 1 equals 1, u2 of 1 equals minus 1. Remember, two vectors are equal if and only if their components are all equal. So the first components being equal is this initial condition. The second one's being equal is this initial condition. And so it's one initial vector for these two initial conditions. And here's why this one is equivalent to this, right? Matrix multiply this times this, plus this times this is precisely what you see here is equal to this, right? This times this plus this times this is precisely what you see here is equal to the left-hand side. So we just wrote it in this compact matrix form. That saves us a lot of trouble because these get real clumsy in the long run. I should make one other comment too here. If it turns out that the right side actually doesn't depend on t at all, right? So it's just a function of u. Maybe these a of t and f of t are just constants. We call that an autonomous system. And autonomous systems are studied both linear and nonlinear. But I'll just throw that term in there because you will hear that term once in a while. Those are important equations as a subclass of differential equations. Well, let's see. One more important point is that higher order differential equations actually can be written as systems of first order equations always. And so all those things we were doing with second order, fourth order equations and so forth, we could have simply rewritten them as first order equations and studied them in this context. In fact, some of the theorems, like the existence uniqueness theorem for higher order equations, is proved in a lot of textbooks by rewriting them as first order systems and applying the theorem for first order equations applied to systems. So these are very important for proofs as well as for systems of nth order equations. Not every system of n equations can be written as an nth order equation, at least trivially, but we can take every nth order equation and rewrite it as a system of first order equations with the same trick. And actually it's a very important trick because in numerical methods where you try and approximate solutions on the computer, this is what people almost always do. You let u1 equal y, the dependent variable you're trying to solve for, so I'll use y instead of u here. And then you let u2 equal dy dt, u3 be second derivative, all the way through un is the n minus 1 derivative. And then if you have this differential equation, depending on where the nth derivative is written, you're written in normal form. The nth derivative is a function of t, and the first y and its first n minus 1 derivative. Making this substitution does what? Well, it allows you to rewrite this single equation equivalently as this. du1 dt is u2. That's just saying that right? Derivative of u1 is dy dt is u2, right? So that expresses that u2 is the derivative of y. And then du2 dt equals u3, that's just expressing the second equation, u3 is the second derivative of y. And all the way down until the very last one, though, you say that un, oh, I'm sorry, after you do the last one, you say that the differential equation itself, dny dtn, well, that's derivative of un, which is the nth minus 1 derivative, is equal to f. Well, f is, you just replace the y's with these various derivatives. And so this system is equivalent to this single nth order equation, but this is a system of first order equations. And actually all of them except the last one are just expressing these relationships between the derivative, and then the last one refers back to the differential equation itself. Well, having written this down as equivalent to this nth order equation, we can now write it in matrix form since it's a first order system, right? And here's what it looks like. Well, you see du1 dt equals u2, dun minus 1 dt equals un, and here's the differential equation, dun dt equals f, now, however, provided that the original differential equation was linear, the system of first order equations will also be linear, because, let's write it down here, here is a general nth order equation, linear equation. Remember this? This is how we define nth order linear equation, a single one. If this is my single nth order equation, I just make this substitution, and the first equation says du1 dt equals u2. Well, that's what I get, nothing plus u2 plus nothing plus nothing. That's what this first equation says, written in this form. du2 dt is supposed to equal u3, right? Well, it's equal to 0 plus u3 plus 0, 0, 0. And so all these equations are expressing these, and then the last one says dun dt equals, well, you drop these things over on the side. You got minus pn minus 1 times the n minus first derivative, which was un. Let's see. And so you got, oh, I wrote these coefficients in reverse, did I? Let's see. This should multiply the n minus first derivative here, which is un. So I wrote these in backwards order. It should be minus p0 minus p1 to minus pn minus 1. And you multiply all those, I'll fix that on the handout. And so you multiply all these together and then add f hat, and precisely you got this equation. So this is just the matrix form of this equation. That's all it is. And here's an example of that. Let's look at a third order differential equation and write it as a first order system. If it's a third order equation, it will convert into 3 first order equations. If it's a 10th order equation, it will convert into 10 first order equations, just because you can see it straight from the substitution. Here's what we do, and then for a third order equation, that the existing uniqueness theorem requires that we have 3 initial values, we recall, from solving these before, and these will translate into an initial vector. So here we go, we'll divide this through by t, first to put it into standard form, and it looks like this. And now we'll make the substitution we said. Let u1 equal y, let u2 equal derivative of y, u3 equal the second derivative of y. And then this single differential equation becomes that. du1 dt equals u2, du2 dt equals u3. And du3 dt, this one, right? u3 is the second derivative, so this is the derivative. The second derivative is the third derivative. Plus 2 over t times the second derivative, plus 5 over t times the first times y, that's u1, equals 6. We've rewritten this equation as this system of 3 linear equations. And there it is in matrix form. You just write it out. Right? du1 dt equals nothing times u1 equals u2 plus nothing, right? So it says this equation, and then du2 dt equals u3 becomes 0 plus 0 u3, sure. And similarly, then the differential equation, du3 dt, and I put these over on the other side here, and you get minus 5 over t u1, minus 2 over t squared u3, and then plus the 6 over here. And these initial values that we had, that u1 of 1 equals 0, u2 of 1 equals 1, u3 of 1 equals minus 1, corresponding to the conditions on the derivatives originally. So there's how you write a third order equation as a system of 3 first order equations. And then you can look at this and say something very nice about it. All these elements in here are continuous except where t equals 0. So you'll get, and same thing over here, so you can guarantee by the existence uniqueness theorem there will be a unique solution on any interval that doesn't include t equals 0. Now which interval do we want? Well, our initial value is given at t equals 1, so this problem gives a unique solution on t greater than 0. It has to be, you can take the largest interval you can that includes the initial point, initial t value, and excludes all the discontinuities here at t equals 0.